Hi, we are the first press team, WinnieTheBest, from National Taiwan University. Our task is multimodalities record recognition. Here is our agenda. We'll briefly introduce the task and the dataset, then talk about the approach we proposed, and finally we'll talk about our conclusions. Modalities recall presents a challenging task of finding the most relevant product images given a search query in natural language form. Our approach achieved 0.785 and 0.848 NDCG85 to be the first place on the private leaderboard and the third place on the public leaderboard respectively. The dataset consists of product image embeddings and text query pairs with additional image information such as the number of bounding boxes and image classes. A critical issue of this task is that the training dataset only contains positive pairs. We'll elaborate on how we deal with this problem later. We move on to our proposed approach, which will be separated into three parts. First, preprocess, to construct features for model to learn. Second, I'll talk about our model architectures. Lastly, post-process. We'll introduce how we post-process the predictions from the model trained. First, we introduce the detail of preprocessing. For raw text of queries, we find many queries in text A with weird grammar, such as B word to be the first word, which will harm the performance of the contextualized embedding such as bird. Hence, we filter out such words to make a query more like a sentence. As for the image feature, instead of using the original 2048 dimension feature directly, we additionally concatenate box feature and label feature. The former consists of 6 dimensions including 4 dimensions of given box position normalized, and 2 dimensions of normalized area and aspect ratio. The latter is 33 dimensions feature trainable with an embedding layer. Negative sampling always play a big role in machine learning tasks, which will directly influence the quality of training data. So here is our proposed method. From validation set, we can see that the candidates of a query usually have similar words. We thus give higher sampling probability to the query sharing same words with the positive query. However, it is not easy to tune the probability distribution. Also, another annoying thing is that the sampling ratio of similar queries can be neither too high nor too low for a model to learn. Therefore, we come up with an easy tuning method. Firstly, we find the top k most similar queries, sharing most words for each query. Secondly, for each query, we sample queries from its top k most similar queries with the same amount of the number of the query. Thirdly, for each sampled query, we uniformly draw one feature to be negative. Finally, repeat the second and the third step k times. By the above method, all we need to do is tune top k, which we set to be maximum of numbers of features of queries multiplied by 3. Due to the tremendous size of training data, we cannot train a single model to the very full extent. To handle this challenge, trying to increase diversity of models as much as we can will be an efficient and effective solution. Therefore, we mainly train 2 different types of models, MCAN and VisualBird, as first level model. First, we introduce the detail of MCAN. The model consists of multiple MCA layers cascaded in depth to gradually refine the attained image and question features. The MCA layer is a modular composition of the 2 basic attention units, the self-attention unit and the guided attention unit, utilizing the scaled dot product attention. However, there are two differences between the original MCAN and ours. First is that we replaced the word embedding parts with Roberta's word embedding layers. Second is that instead of adding the two flattened features of image and text, we concatenate them. Moreover, to capture more information, we additionally concatenate the multiplication and non-one distance of the two flattened features. As for learning rate scheduling, at first we used linear schedule, but we found that the performance will be stuck for several epochs during the last period of training. As a result, we modified the scheduler to be sine wave, and it turned out that the validation score increases stably. And here is the parameters of MCAN. Next, we introduce the details of Visual BERT. Visual BERT merges the image and language features as input for the BERT model. Image regions and language are combined with a transformer to allow the self-attention to discover implicit alignments between language and vision. Well, different from the cited paper, in order to distinguish between the image features and the language features, we use token type iris embeddings with separate token to separate the two features. And the learning rate scheduler is the same as MCAN's. Finally, we post-process the output of transformers. Since the above training process doesn't use the information of valid, which is the only ground truth we have. Therefore, we extract the embeddings from the trained first level models to be the downstream classifier's input, and use 0, 1 as training targets to generate our final logics. Here we use LightGBM with all its default parameters. Next, for ensembling, totally we have 55 MCNs and 14 visual BERTs. We simply add up the predictive logics from downstream classifiers to ensemble all models. Besides, there is another observation from validation, which is that the products with less appearance are more possible to be the answers. Therefore, we filter out all products occurring more than once, then rank the left product's logics to get our final prediction. To sum up, in this paper, we have introduced an empirical framework for the Multimodalities recall competition of the KDD Cup 2020. Our team WinnieTheBest was ranked the first place on the final leaderboard. In our solution, we first conduct an easy tuning negative sampling method. Then, we train two different kinds of first level models to generate embedding for classifier to learn. After that, we train LightGBM on our only ground truth data. Finally, we ensemble 69 trained models by summation and filtered out high-frequent products. Nevertheless, there are still some space for further improvement. For example, further pre-trained word embeddings on product-related datasets may give improvement on performance. In addition, some problems remain untouched in our paper, such as the time efficiency in processing queries. We leave this challenge as our future work. Here is the acknowledgement and reference. Thanks for your attention.